Bismillahirrahmanirrahim. This is our lecture number 14. And we discuss special types of wave functions, that is the sinusoidal wave, because mostly the transverse waves are represented by the wave functions of the sine or cosine shape. So let us discuss about the sinusoidal waves. In the last lecture we had discussed about the general wave function, that the wave function in general should be of the shape of f of x t is equal to f of x minus vt. So the particular types of wave function, that is the sinusoidal waves, have important applications. So let us describe these types of wave functions. Let us consider over here at t is equal to 0, we have a transverse wave train along a stretched string given by the wave function y of x0 is equal to ym sine of 2 pi by lambda into x, where lambda is the wavelength and x is the position at any position at which we are observing the wave. Ym is the amplitude of the wave. So the shape of the wave is shown in this figure. Ym represents the maximum displacement of a point from its equilibrium position. This is the amplitude. At t is equal to 0, the blue curve, and after time t is equal to some time t, we have the red curve. The red curve has slightly shifted towards the right from the blue one. That is, the wave is traveling with a speed v towards the right, and the shape of the wave is a sinusoidal shape. The value of the transverse displacement is the same at any x as at x plus lambda, x plus 2 lambda, or x plus n lambda. That is, after every wavelength you will find the same displacement, vertical displacement on the x-axis. That is, at x is equal to 0 you have a 0 displacement. Similarly, at x is equal to 1 wavelength, that is lambda, you have again the same displacement, and so on. So where lambda is the wavelength of the wave, and if the wave is moving along the positive x-axis with a phase speed v, then the equation of this wave this wave becomes y of x t is equal to ym sine of 2 pi by lambda into x minus vt. At t is equal to 0, this will be just 2 pi by lambda into x as t is equal to 0. But at any arbitrary time t, the wave should have a shape ym sine of 2 pi by lambda into x minus vt. This equation is of the general form y is of x t is equal to f of x minus vt. That is, the function f is now a sine function, and the argument of the sine is x minus vt. The period t is the time required for any particular point x to complete one cycle of the transverse motion. That is, on a stretched string, every point or every particle oscillates in a perpendicular direction to the propagation of the wave. So the time period t is the time during which every particle completes one oscillation, and in this time the wave will travel a distance v into t, where v is the speed of the wave and t is the time period, and this vt distance must be equal to the wavelength of the wave, that is lambda is equal to vt. As we know that the time period is the reciprocal of the frequency, so we can write lambda is equal to v divided by f, or v is equal to f lambda. This equation establishes a relation of the frequency and wavelength of the wave in terms of the phase speed v. So using equation 3 and 2, we have another expression for the same y of x. Before we had written an equation y of xt is equal to ym sine of 2 pi by lambda into x minus vt. Now we can put that lambda inside the argument x by lambda minus vt by lambda. Now from the above equation, if we use equation 3, lambda is equal to vt, so we can write the y of xt is equal to ym sine of 2 pi into x by lambda minus t divided by t. And as we know that 1 over t, that is the frequency, is equal to v divided by lambda. So equation 5 shows that at a particular time, constant value of t, y has the same value at x and x plus lambda, x plus 2 lambda, and so on. To elaborate the above statement, let us replace x by x plus n lambda in general. So look at the equation. Y of x plus n lambda and t is equal to ym sine of 2 pi into x plus n lambda divided by lambda minus t by t. Over here we see that the equation becomes 2 pi x divided by lambda plus 2n pi minus 2 pi by t into t. So we see over here at the last that we have an equation of the shape ym sine of 2 pi into x by lambda minus t by t plus 2n pi. So let us call this angle as alpha and this one as beta. So this is ym sine of alpha plus beta, and if we use the angle identity sine alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta, we have a relation, this one y of x plus n lambda and t is equal to ym sine of 2 pi into x by lambda minus t by t into cos of this. So finally we get y is equal to sine of 2 pi by lambda into x minus vt, or 2 pi into x by lambda minus t by t, which is the same as for y of x over t. So if you add any integral multiple of lambda to the x, you have the same displacement y, and the same vertical displacement y, that is at any position x and x plus lambda, x plus 2 lambda, x plus 3 lambda, and so on, x plus n lambda, you will have the same vertical displacement. Now if we fix our position coordinate, that is the x, so what we will get, the displacement y at a particular x has the same value at time t, t plus 1 time period, t plus 2 time period, and t plus n time period. Yani if we have at a particular position x, say x is equal to 0, we have a displacement y, then after time, one time period, two time periods, three time periods, four time periods, and n time periods, we will have the same displacement at that position. So to verify this mathematically, let us look at the relation y of x and now replace the t, the time coordinate, with t plus nt, capital T. So this is ym sine of 2 pi into x by lambda minus, instead of t you have to write t plus nt. So this is equal to sine of ym sine of 2 pi x by lambda minus 2 pi t by capital T minus 2n pi. Again you have two terms in the arguments. One is this one and the other is this. So let us call it alpha and this one is beta. Again use the angle identity of sine of alpha minus beta. So we get over here the same result, that is y of x over t plus nt is equal to y of x over t. Yeah, that is at a particular location, if you have some vertical displacement, so after adding any integral multiple of the time period, you will have the same displacement y. In order to reduce this equation from the so many terms to a very simple equation, so let us define some terms, and these terms are the wave number, which is 2 pi divided by the wavelength, and the angular frequency, which is 2 pi times the actual frequency f. So 2 pi f or 2 pi by t, this is known as the angular frequency, while k is known as the wave number. The wave number will be measured in radians per meter, while omega should be measured in radians per second, because this is 2 pi is angle, and in the denominator you have time, so per second. Thus equation 5 can now be written as ym sine of kx minus omega t. This is the same equation as the above one, that is in which we have x, y, lambda and t by t, but representing a wave moving along the positive x-axis having the wave number k and the angular frequency omega. If the same wave moves along the negative axis, then you have to replace the minus sign with a plus one. So Vs, the phase speed, and often called the wave speed, and how it is related to the angular frequency and the wave number. So we can get it from the lambda by t relation, and you can see that V is equal to omega divided by k.